Yeah. Yeah. So if you're on the tutorial,
if you can turn up your audio, not your audio on your computer or something, or someone have the audio.
is it good now? Nope.
Where is the audio coming from?
I'm not sure. Somewhere. Okay, so no more reverb?
Yeah.
Cool. So if you're on Origin tutorial and you've installed it correctly, this command should not throw any errors. So I'm going to check out to the unfinished version. Okay, so while people are still installing these last two, I guess I'll just start with like a brief explanation of how Plasma works. So Plasma is a layer 2 scaling solution, and it was originally intended for Ethereum, but it can work for any Turing-complete blockchain. So the way it works is that users deposit funds onto a root chain, in our case Ethereum, and as soon as they deposit, we wait for that deposit to get finalized. And once that happens, you can then start spending your deposits on the sidechain, where your transactions can go through much faster and you'll have much lower fees because there's less traffic on a separate sidechain. And you can transact on there, and whenever you want, you can exit back onto the root chain. And the thing that's interesting about Plasma is that your funds are safe even when the operator is malicious. And the way that works is because we have a confirm sig that when users send money in the sidechain, that transaction gets included. And then once the transaction gets included and the user validates that, yes, my transaction was included and everything was valid, nothing malicious happened, then they send a confirm sig to the receiver. And only after that point is the transaction considered final. So in that way, you can always exit the sidechain if the operator is being malicious without having any of your funds stolen. So at Fourth State, we built our Plasma MVP sidechain with the Cosmos SDK. So hopefully in the next 2.5 hours, we can actually start building like the SDK part of the sidechain and then deploy what we've built. So yeah.
I work at Fourth Street. I'm not very familiar with the company, but are you trying to build a Plasma chain just because you want to build a Plasma chain, or is there an end goal which Plasma solves?
The end goal is scaling the Ethereum blockchain, or whatever the root chain may be. So blockchains right now are incredibly slow. So Plasma is one way to scale them without compromising too much of the security aspects of blockchains. But there are also like specific use cases that you might think of where Plasma would be.
The scenario you're thinking of is the root chain in this scenario is Ethereum.
Yeah, for us.
Side chains based on Tendermint Cosmos.
Correct. Our sidechain is running Tendermint consensus.
Thank you.
Yep, no problem. And feel free to interrupt me with questions if you have any. So, yeah. Okay. The stuff that you need to install is on the README if you still haven't, but I'll start going from just starting to build it. So whenever I build a SDK chain, I always like to work from the bottom up. So that means starting with the messages that you actually send to the blockchain. So for that, the SDK has an interface called sdk.message. And that's usually what I start by filling in. So for us, we only have one message that we're sending around on the blockchain. We're sending a spend message, which is a spend of a maximum of 2 UTXOs, and it outputs a maximum of 2 other UTXOs. So do people know what UTXOs are, or should I explain?
Spend transaction hours.
Yeah, so every transaction that gets included creates transaction outputs, and when you spend them on the sidechain, you're spending those outputs to create new ones. So on the Plasma MVP sidechain, we have each UTXO specified by its position. So we have block number, which is the block number in which the transaction was included. Transaction index, which is the index in which that transaction was included in the block. So the first transaction in that block has TX index 0. The second transaction in that block has TX index 1, so on and so forth. And then for us, we have a maximum of 2 UTXO outputs per transaction. So that's what we have in the O index, where if you're the first output, you're 0. If you're the second output, you're 1. And then sometimes people are spending deposits directly from the root chain. And if that's the case, then these 3 fields are 0. And this deposit represents the nonce that's being spent. So each deposit has a unique nonce that represents that deposit on the root chain. And so when you want to spend that specific deposit, you just specify the correct nonce here. So if we wanted to spend 2 UTXOs, what fields might we want in our spend message? So we would want to spend, because each UTXO is specified by a position, we would want to include that position in the spend message so that our application knows what UTXOs are supposed to be spent, right? So the message should include all the fields that are needed for the application to change the blockchain state without any authentication data. So in here, one thing would be block num 0, UN64. So this would be the first block number. It would be the block number of the first UTXO we're trying to spend. You'd also have TX index 1, which I'll make a UN16 because in our implementation, we only have 2 to the power 16 transactions per block. So this would never go above 2 to the power 16. So it's a UN16 there. And then output index, it's either 0 or 1, but I'm using a UN8 to represent it because the encoder that we have doesn't allow us to use booleans. So that's kind of just a RLP specific thing. And then in case we aren't spending a regular transaction, we need this deposit num as well to specify whether we're spending a deposit. So we can put that in there, which is also a UN64. So does this part make sense, where we're just specifying the fields that would let the application know what UTXO we're trying to spend? So this, so if I'm trying to spend a UTXO in block 1 with transaction index 5, it might be 150 at 0 would be the UTXO that I'm trying to spend. Does that make sense? Okay. Also, I'm going to include the owner here, and we'll see why in a second. But the owner is an Ethereum address, so I have go Ethereum/common imported, and I can just write common.address, and that'll specify what the owner of the first input is.
Sorry, having some problems with installing the Go.
Okay.
And that's been, I feel like I might not be the only one.
Mm-hmm. So have you tried go get and then just github.com? So if you try go get github.com/AdityaShripal/Plasma MVP sidechain. That
with just the link that you got there?
yeah, without the https:// That should hopefully run it. Could you double check that Go is installed by just running Go and seeing whether that command even exists?
Yes, it's Go
Okay.
commands.
So if you run go get, it should copy this repo into the correct place. So go get github.com /plasma MVP. Cool, it worked?
Yeah.
Awesome. And if you want to follow along with the unfinished tutorial, then you would just git checkout tutorial-unfinished, and that'll remove all of the finished stuff so that it's filled with to-dos.
Okay.
Cool. So git checkout space tutorial-unfinished. This part. Once you CD into Plasma MVP sidechain. So are you CD'd into Plasma MVP sidechain?
You said go get or go?
No, just git space checkout
Sorry, my terminal isn't returning, so I'm not sure what's happened.
from go get.
Yeah, from go get.
It's not returning.
Yeah.
It's taken a while.
Okay.
That command could take a little bit because it's got downloaded a bunch of stuff.
Yeah. So yeah, it might be the internet's just slow, but once you're done with that, you can git checkout to tutorial-unfinished. So you might want to just copy that command down,
Right.
and that'll just get you back to the unfinished tutorial. But does anyone have questions on like this part so far?
I understood the data structure, but
Yeah.
I don't understand why we're making the data structure.
So this is the message that'll get sent to the blockchain. So so when I want to spend a UTXO, I construct this spend message, which will have the information on what UTXOs I want to spend and to whom, right?
Okay.
So if I want to specify what UTXOs I want to spend, I need to give it the position. So the position of that UTXO is these 4 fields.
And this is
So that's
this is transactions in your blockchain.
correct.
Sidechain.
This is on my sidechain.
Yes.
I want to give the spend message to the blockchain, and then once the blockchain receives this spend message, it should be able to tell, okay, here are the UTXOs this user wants to spend, and here are the outputs that I need to create from it.
So you started from the message you're going to send, and you haven't yet modeled the state of your
Correct, correct. So I generally start with messages and move up. So this would be the first UTXO input that I would want to spend, and then I'd want to spend a maximum of 2. So I would just replicate this state with, with the second input. Okay, so this specifies the 2 inputs that I want to spend completely. So these fields will let the blockchain know which UTXOs I want to spend. But now I want to specify who I want to spend them to, right? So does anyone have ideas of what the additional fields might be?
What am I checking out? You have a from and a to account, I assume.
Yeah, so you would so this would be the 2 addresses, right? So I could do new owner 0. Do you have a question, by the way? Sorry.
Yes. So
Yeah.
git checkout what now?
Tutorial-unfinished. So new owner 0, and there are 2 possible outputs. And there's one last thing missing here, is I haven't specified how much money each of these people are going to get. So for example, like this UTXO position might have 100 Ether in it, but I might want to spend 50 to new owner 0 and 50 to new owner 1, correct? So just to represent that, we would need like amounts for both of my outputs. So to fully create this message, I would need 2 amount fields. And now I'm done with my spend message. So this has all of the data the blockchain needs to figure out which UTXOs I need to spend and which UTXOs I need to create. It doesn't have any authentication data though. So anyone could create this, even if they don't own the input UTXOs. So from here, we would want to implement the rest of SDK.message. So spend message is an implementation of the SDK.message interface. So as part of that, it has methods type or route, which I filled in for you. They're just strings. Validate basic does sanity checks on the message to make sure that the message isn't malformed, and so that any full node could easily reject any message that doesn't pass validate basic. And then get sign bytes will tell us what bytes our addresses need to sign over. And then get signers tells us which addresses would need to sign our message. So any questions on the interface?
RLP is an encoding format?
Yeah, RLP is the encoding format that Ethereum uses. So we need to be compatible with the Ethereum root chain, so we use RLP as well. So does anyone have ideas on what sanity checks we might perform on our spend message? So what would be a malformed spend message?
Well, you should check out whether the balances are working out, right? User spends.
Okay, that's a good point, but we can't do that here because we only have the output amounts. The input amounts aren't specified. They're in the blockchain state. So we will do that, but just not at this stage.
Okay.
So at this stage, just looking at the fields here, what can we say is a malformed message? So, well, the first input would need to be filled in, right? We can have a 0 on the second input, where someone isn't using the second input, for example. But the first input clearly should have some position, should specify some valid position. So that's one sanity check we could do. Another is making sure that the owner is filled in, so it's not just a 0 address. And then making sure new owner is filled in as well. So those would be like examples of sanity checks that we could do just at this stage. So I can just copy over the validate basic, and I'll go over what it does. Okay, so this just checks that the message.owner, the first owner, is valid. It checks that the first new owner, the to address, is valid. And then here it makes sure that I'm not trying to spend the same position twice. So if this was like 1000 and 1000, obviously that would be invalid. You can't spend the same UTXO twice. So that's another sanity check we could perform. And then if the deposit num is non-zero, then these 3 fields should be 0. And if these 3 fields are non-zero, the deposit num should be 0. Because you're either spending a deposit or you're spending a UTXO that's already on the sidechain. So it can only be in one of those 2 states. So that's another sanity check we could perform. So that's what's being captured by this validate basic. And yeah, also the first amount should be non-zero. And if any of those cases are not true, then we can return an SDK.error. And I've defined some of them already here. So there's error invalid address, invalid amount, and we can just return those in validate basic. So get sign bytes was already implemented because we're using RLP. So who would need to sign this message? So for a given spend message, who should be signing the message?
Well, the sender should sign it, so it's
Right.
first account.
Yeah, so it's owner 0, and if this if the second input is non-zero, then the second owner needs to also sign it, correct? Because it could be 2 different owner addresses. So we have 2 inputs, 2 possible inputs, and 2 possible outputs in our UTXO model. So the first input is always filled in. So owner 0 signs, but if this is filled in as well, then owner 1 would need to sign it as well.
But how would that work from a client input standpoint? Would the first owner sign it and then forward the message to the second owner to sign it?
In this case, like practically speaking, it would be like 2 addresses owned by the same person.
Oh.
So it would be like, yeah, both addresses would sign over the message. Yeah. But theoretically, it could be owned by different people too. It would just have to be some weird sending over the half-signed message. But that's not like a use case we're necessarily thinking about. So yeah, that was exactly the right answer though, is the first owner, and if the second input exists, then the second owner. So I'll just copy over this and explain what it says. So that's exactly what this code does. It sets the first address to message.owner0, and if the message.owner1 is not the 0 address, meaning there is a second owner, then we append his address as well. Does that make sense? Cool. We'll skip this for now. I'll get back to it. But SDK.tx is the next step on our building strategy. So SDK.message has all of the data that we need to send to the blockchain, but it has no authentication. So there are no signatures in this struct. So what we want is to put all of our authentication data into the transaction. So you can see the base transaction already has a spend message inside it, but it would also need authentication data. So what would the authentication data be here?
Signatures from all the signers.
Correct. So it would just be the signatures. We're using, so a signature is 65 bytes, and there are 2 signers. So it's just 2 65 bytes. If there happens to be only 1 signer, right, in the case where message.owner is 0, then we just fill in the second part of it with 0 bytes. The reason we do that is because just to keep simplicity on the root chain. So in this way, like the transaction always has the exact same structure, regardless of what's happening inside of it. Cool. So, and then this get signatures is just a getter method to return oh, my bad. So this get signatures method just returns the signatures. And SDK.tx has a method called getMessages, which will return an array of SDK.messages. But for us, every transaction has only 1 spend message. So we just return the spend message encapsulated inside this array. Does that make sense? Cool. Now, yeah. So that's kind of concludes the messages and transactions that we're going to be sending around to the blockchain. We also, in our repo, have like a UTXO module. A lot of it's filled in, so I'll just go through it. So we have this UTXO struct, which will be stored in the blockchain state. So here the address is like the owner of the UTXO. The amount is how much money it holds. Denomination is, in our case, always Ether. Valid just denotes whether it's spent or not. So an unspent UTXO would have a valid equals true. A spent UTXO would have valid equals false. And then the position, which is, as I said earlier, block number, transaction index, output index, and deposit number. Cool. Yeah. So inside our UTXO module, we also have like the spend message interface, which just wraps an SDK.message interface, and it has these two additional methods, inputs and outputs. And that'll just tell us what inputs this spend message is spending and what outputs this spend message is creating. So that was what these two methods were before that I briefly skipped over. So here not here. Here we're creating the inputs. So in this case, there are a maximum of 2 inputs and a maximum of 2 outputs. So these two methods are implementing those 2 methods from the UTXO module. Cool. The last thing I wanted to show you on the UTXO module for now is the mapper. So the mapper is a way to interact with the blockchain state. So inside the Cosmos SDK, we have like stores where we can store our UTXOs. And this mapper just makes it much more easier to interact with the store to get UTXOs and receive and spend them. So the base mapper struct has an SDK.store key inside it. And with the SDK.store key, that allows this base mapper to access the UTXO store. So without this key, it would not be able to access the UTXO store in our blockchain state. And it also has a codec for encoding and decoding this UTXO from the store. So an example of how this would work is that, like, if you look at the getUTXO method, it grabs the store by passing in the context key that it has into the context, which has all of the blockchain state stored in it. So once it gives the key to the context, it can now access this store. And then the store is basically a key value dictionary, where for us, the keys are the address and position appended, and that's the key. And the value would be the encoded UTXO. So if you give me the address and position, I can give you the UTXO that corresponds to it. So that's what this is doing. It creates the key, gets the encoded UTXO, decodes it, and then returns that UTXO. So there are similar other methods. They're kind of just tediously bringing information from the store and decoding it, or encoding information and storing it in the store. So we have receive UTXO, which will take a UTXO and put it in our store. We have spend UTXO, which will take an address and position and mark the given UTXO at that location as invalid because it's spent, right? And then store that updated UTXO back into our store. So does anyone have questions on the mapper? It's mainly a way to interact with the blockchain state. Cool. We'll see how we use it later. Yes?
Position,
I'm sorry?
Position, what is it?
Yeah, position is the position. So each UTXO has a unique position that's specified by, I have it here. Yeah, so these 4 fields specify the position. So block number, transaction index, output index, and deposit num. And so what we do is we have the owner and the position appended together, and that creates like the key in the store, and the value is the UTXO. Cool. So with that in mind, this is like the next layer up on our blockchain, and it's the anti-handler. And what the anti-handler does is it takes in the context, which has the blockchain state, the transaction, which we defined earlier. It was the base transaction with the message and the signatures. And then what it returns is an SDK.context, possibly modified, a result that basically says, it's either failed, like this anti-handler has failed or it's passed, and then abort, which will be true if the transaction has failed. So the anti-handler's job is to do all of the authentication, checking, and validation before we move on to actually updating the blockchain state. So that's the purpose of anti-handler. Does anyone have questions on what the anti-handler does?
Is there a reason you called it an anti-handler?
Anti-handler is what the SDK calls it. Anti, like, because you ante up in poker. It's like before handling. Yeah. That's just the name that they chose. But what we would want to do here is first, we're getting a SDK.tx, which is an interface. But we know that every transaction in our blockchain is a base transaction. We don't have any other SDK.tx's. So what we're going to do is just cast it to types.basetx. And if it's not OK, we return an internal error. TX must be in form of basetx. So what are some like authentication stuff that we should be doing in the anti-handler? Like a pretty obvious one would be to check signatures, correct? So we would want to make sure that all of the signatures match in the anti-handler. So what we would do is I have a helper function here, process sig, that takes in an address, a signature, and then the bytes that it's signed over, the bytes that it's supposed to sign over, and it'll return an SDK.result where it'll return error unauthorized if the signature failed, and it'll just return like a passing result if it passed, if the signature is correct. So I would want to do that for the first signature, so that would be process sig. So from the base TX, I can pull out my message, right? So base tx.get messages. The get messages gives me a list of messages, and my first element is the spend message. And then I can just cast it. So I cast it in spend message. If that cast fails, then we throw an error. And then what I would want to do is process sig on my first signature. So my first signature's address is owner 0, correct? So that would be spend message.owner 0. And my signature is the first signature in my transaction list. Oh. And the bytes that he was supposed to sign over was already defined in my transaction. It's spend message dot get sign bytes. And so if the result that I get is not OK, meaning it threw an error, then I can just return with that error. And the abort variable is true. So does anyone have questions on this step where I process the signature? Cool. Then I would want to check that the UTXO actually exists in my store. So for that, I have a helper method that we can fill in. So check UTXO. What we want to do is check that either the UTXO already exists in the sidechain store, or it's an unspent deposit. So the way we would check that is I have this deposit exists function that will make a query to my Ethereum root chain to see if that deposit exists. So I can say if the position that I'm trying to spend is a deposit and it doesn't already exist, what I would want to do is So I'm given the UTXO mapper that I showed you earlier in this thing, right? So what I want to do first is get the UTXO from my blockchain store. So for that, I would just pass in, to get UTXO, I pass in the address and the position. And so what I want to do here is check that the position if the position is deposit and so what this does is just checks that the position is a deposit and it doesn't already exist in my blockchain store. So that's what this is doing. Because if the UTXO doesn't exist, it'll just return this like empty UTXO struct. So I can check for that. If that's the case, then what I would want to do is check that the deposit does exist. So I can write deposit, comma OK. And then cool. So what this does is I give it my deposit nonce and then also the connection to my Ethereum node. And it'll query the Ethereum root chain to see if this deposit really does exist. And if it does, it'll give me the deposit. If not, it'll set this OK variable to false. So if not OK, then I would return some error. So I can just write that in for now. Otherwise, one thing I do want to check is that the deposit's address is equal to the input address. So I can check so what this is checking is that the person who's trying to spend the deposit actually did create the deposit. And then the other case that I'm looking for is that the the position is not a deposit. In that case, input does exist or should exist, and then I can just check input dot if not input dot valid. So here I'm checking that has this UTXO already been spent? That's what this is saying. Because if my mapper.getUTXO returns a UTXO, then if it's unspent, then valid will be true. And if it has already been spent, then valid will be false. So if it's already been spent, you can't spend it again, so we want to return an error. And if all of these checks pass, then we just return a OK result. So I'll just copy in like the code that does all of the stuff I've copied so far. OK. So that's what this code is doing. So if not OK, deposit UTXO does not exist. And then I check that over here. I check that the input address is equal to the spender address. And then if the input is not valid, then I return that the UTXO trying to be spent is not valid. And then I give the position. Does this part make sense, what we're trying to do here? Cool. So in the anti-handler, I'm using this check UTXO to basically do those two checks. Check if the deposit exists, and if it's not a deposit, then check that the UTXO is valid to spend. And then the last thing that I have is, has TX exited? So this I already have in. All it does is make sure that, so UTXOs that are on the sidechain can be exited, right? So if you've already exited onto the root chain, you shouldn't be trying to spend your UTXO on the sidechain anymore. So that's what this is checking. If you've exited your UTXO, then you're not allowed to spend. So if hasTX exited returns true, then we return an error. Cool. Yep. And then what this does is if the position is a deposit, then we just add, we dynamically just add that UTXO into our store because we've checked that the deposit already exists. And so we can start adding it into the store before it gets spent. Right. So utils.valid address. So this is just checking if the second input is filled in, this line. And what we would do is the exact same checks that we did for the first input. So again, we would run process sig. This time, what fields would we put in? So we need to put in the address. Which address signs in the second input? It would be the second owner, right? The owner of the second input. So that would be spend message.owner1. The signature is the second signature on our. It would be the second signature on our signature list, and then the bytes that you're signing over is the exact same. So you're still signing over the encoded encoded message. So does this part make sense? Cool. We would still do the same checks that we did here. I think those are already written. Yep. So this does exactly the same checks that we did for the first input. OK. So now there's still one last check that we want to do in anti-handler. Does anyone have an idea of what that might be? So we've checked that input 1 is valid and exists. We've checked that input 2 is valid and exists. There was a suggestion on what we might want to do in validate basic that could come up here again.
Check the balances.
Exactly. So in validate basic, we didn't have what the input amounts were, right? Because that was stored in the blockchain state. Over here, we do have, we can check, we have the context for us. So because the context is passed in for us, we can check what the amount is for our inputs. So this is where we would want to check whether the sum of our inputs equals the sum of our outputs. Cool. So to do that, we would want to add in the inputs. So yeah, so for underscore comma input. And here we can use the methods that we've built before. So here I'm iterating over the spend messages inputs. And I can get I think that's right. So let me just double check. Yeah. So the input has an owner and position. So I can iterate over the inputs, get the UTXO that is specified by the owner and position using my mapper functions. So mapper.getUTXO, input.owner, input.position will return the input UTXO. And I can just write input amount equals 0. And what I would want to do here is input amount plus equals input UTXO dot amount. So what this is doing is it's just adding up all of the amounts that I have on my inputs. Cool. And I can do the same for the outputs. Actually, here I can just do it much more easily, where I just say output amount equals spend message dot amount 0 plus spend message dot amount 1. So these are the two output amounts that we had before. So just these two will specify the total output amounts. And then what I can do here is if input amount not equal to output amount, then I would want to throw an error, right? Because I don't want this transaction to go through. So I can return I believe it's so this is just creating an error. So I would create it in like a default code space, which is just a number. And then I would say inputs do not equal outputs. I'm supposed to be returning a result here, and this is an error. So I can just make sure that I return the right type of thing. And I want to abort the transaction, so I set my abort variable to true. Cool. And if all of these checks pass, then I don't need to abort. The transaction went through, so I can return CTX, an OK result, which is just an empty result, and then false for abort. Which means if the transaction gets passed into anti-handler, passes all these checks, then abort is false, and it'll start going into the handler where the actual blockchain state will change. Does anyone have questions on anti-handler? No? OK. So my handler is actually defined in the UTXO module. So here I have the new spend handler. It has a mapper and an X position, which I'll talk about. So a SDK.handler takes in a context, and this time it takes in a message because all of the authentication data is not needed anymore. We already checked it in anti-handler. So it'll just take a message, and it'll return an SDK.result. So here's where we want to actually make the state changes. So obviously the state changes that we want to make is we want to spend all the input UTXOs and create new unspent transaction outputs, right? And save them in our store. Cool. So the first thing we do is cast this message into a spend message. We know that anything that gets into here, into this handler, is a type spend message. If that's not OK, we just panic because there's no reason that it should not be. Cool. So what we can do here is I want to iterate through all of my input messages and spend them. So I can do the same kind of trick that I did in the anti-handler. So I can do for all of my inputs. What I would want to do is spend them. So mapper. So I already have a spend UTXO method. In mapper. So if I show you mapper, there's a spend UTXO message that takes in a context, the address, the position. What it'll do is it'll get the UTXO, change valid to false, and then store that encoded, that updated UTXO back in the store, right? Because we can't just update it and leave because the blockchain database hasn't changed. So what we would want to do is change the UTXO and then encode it and store it back into our store. Cool? So since that functionality is already there for us, all I need to do is call it with the right arguments. And actually, it needs a CTX because that's where the blockchain state is. So that's the context. So this will iterate through all of our input UTXOs and mark them all as false in their valid field, right? So that means they've all been spent at this point, once we cross that line. What we want to do here is create outputs. And this is where the next position comes in. So you'll notice in transaction, while we have the input positions, there's no output positions specified here because we don't know beforehand what the output position will be. That's something that's determined by when this specific message gets processed by our blockchain. So the position of any output, well, with a given message, the block number will be the current block, like current tenorant block number, correct? The transaction index will be the number of transactions that it's on. So if this is the fifth, if new spend handler is handling the fifth message in the block, then transaction index will be 4 because it's 0 indexed, right? And output index is what will be defined by how many outputs there are. So that's something that is specific to how many outputs gets put into this position, into this transaction. Does that make sense? So we need to figure out what the position of our outputs are going to be in this function. So that's why we've passed in our new spend handler a next position function. And we'll see how it's defined later. But I can just say so block number is going to be always the tenorant block number, right? Transaction index at each time this gets run, transaction index should be incremented by 1, right? But for every subsequent output that this creates, transaction index should not be incremented. Does that make sense? Because we haven't created, these new outputs are not the result of a new transaction. It's the same transaction. So the transaction input index stays the same for all of these outputs, and it's the output index that gets incremented. Does that make sense? Cool. So, so on the first input, so I would do, so I'm just going to define a position here, and nope, it's not Python. On my first input, that's where I'd want to increment the transaction index. So it would be next pause ctx, comma, false. And so this secondary flag is just doing exactly that. So if this is set to false, it'll increment the transaction index. If it's set to true, then it's secondary output, so it'll increment the output index and keep the transaction index the same. Cool. So if I equals 0, that's the next position. Oh, so next. And then else, ctx, comma, true. And so now we need to create our UTXO, right? We need to create a new output UTXO. So I can call this so colon equals what did I have here? Oh, I have this function that'll create the new UTXO for me. And its arguments are, if I look here, yeah. So it takes in an owner, an amount, a denomination, which is for us always ether, and a position. So the position is already defined by next. We already know what the position is. And the owner would just be output.amount. Output.owner, output.amount. And my denom is, let me just double check so I don't mess things up. No, this already has a denom field in. And then next. Does anyone have questions so far? So what I've done is for each output, generated the next position that it'll occupy, and then created that UTXO. OK, but are we done yet with handler? So we've created this new UTXO, but it hasn't been added to our blockchain state yet. So that's the next step. So again, this is why having a mapper is useful, because it has a lot of this functionality for us that we don't need to repeat. So receive UTXO will take in a UTXO and add it into our store. So I can just do, I think does new types? Yeah, cool. So new UTXO sets valid to true. So this is an unspent output, obviously, because we've just created it. So all I do here is that, and then we're done. We've finished the state changes. So notice there's actually no checking in handler. We've done all of our checking in ante. So over here, in our case, we can just do the state changes. For some other applications, maybe you might have some state checking even in here. But for us, all of the authentication and checking can be done in the ante handler itself. So here we just change the state immediately without any checks. Because the flow of the application is to always go from ante handler first and then to handler.
I'm not familiar with Cosmos, but I'm familiar with ABCI.
Mm-hmm.
So is ante called in check-tx?
Yes, it's called in check-tx. Yeah, good question. Any other questions? Cool. So now that actually mostly wraps it up. Now it's kind of just putting all the pieces together at the app level. So we can look here. So I'll first show you the next position that I called in the handler functions. So here you can see in my child chain struct, I have a transaction index, which is a UN16. And so I have this next position function, which takes in a CTX and secondary, as we saw. And if not secondary, then we increment the TX index and return with the block height, which is the block number, the transaction index, 0 for the output index, and 0 for the deposit number. And then because we only have two outputs, if secondary is false, then we just write 1 on the output index without incrementing TX index. Cool? All right. So I'll just show you the child chain struct. So here, this is the base app, which is Cosmos's main application that we're extending. We have the codec, which allows us to encode and decode transaction index, which is used in the next position. These two are like store keys. That's how our mapper was able to open those stores, because we gave it access to the store key. The UTXO mapper, which we would need to use. Plasma store, we didn't go over because it's not relevant for this tutorial. And then this information is all Plasma related stuff. So if your node happens to be a validator, this is set to true. The validator address, the validator private key, which would be needed to start submitting blocks to the root chain, because the validator needs to sign over every block that he submits to the root chain. The node URL, which is the URL that you use to connect to your Ethereum node. Block finality, because Ethereum is proof of work, unlike Tendermint. So whenever someone deposits, we don't just accept it immediately. Instead, we wait a specified number of blocks before we consider that deposit final. And only after it's considered final do we allow it to be spent on the sidechain. Cool? And then ETH connection uses the node URL to connect directly to our Plasma root chain contract. Cool. So this new child chain sets up the blockchain with the correct values. So here, right. So what we want to do here is we need a router to route any message that's a spend message to our spend message handler. So in the SDK, you can have multiple messages and multiple handlers. For us, we only have one message, one handler. So it's a bit easy for us. We just do add route. So spend, and spend you'll see is the same as the route method. So, and what we want to route it to is the, where am I? Is the UTXO.spend handler. So new handler, and that takes in new spend handler. It takes in a mapper and the next position. So my app.utxo mapper is already defined, so I can pass that in. And then, cool. So this function, when it gets called, will return an SDK.handler, which can then subsequently take in a context and a message and update the state accordingly. Cool. The other thing we need to do is we have these two stores, the main and Plasma. So we need to mount those stores into our blockchain state. So that just requires these two lines. So I'll just copy them over and explain them. So all this is doing is taking these keys that we had and mounting them into our blockchain, mounting those stores into our blockchain state. So we initialized the handler up here, up here, and routed it correctly. Now we need to initialize the anti-handler. And that's app.set anti-handler. And then now we do auth.new anti-handler. And this takes in a mapper, Plasma store, and a Plasma client. Okay, so that is app.utxo mapper. And then the Plasma client is app.eth connection. Cool. So now this will return an anti-handler, and that anti-handler will take in a context and transaction and do all of our authentication for us. So I believe, there's just one last thing we needed to do before we're done. So have these two things in here. So app.set interchainer, we're not going to go into that, but it runs code that will happen before the start of the blockchain. So in this, we have basically just initializing any genesis state that we have. So that's what this is doing. And then app.set end blocker, this function will be run at the end of every block. So there's one thing we definitely want to do at the end of every block. So if you notice, txindex is a part of our child chain struct. And it starts at 0 in new child chain. And every time we call next position, it increments by 1. So what do you think we would want to do at the end of every block to txindex?
Reset it.
Yeah, exactly. So we want to reset it to 0. And what that does is so that any increments that happen in the first block gets reset on the second block. So we start again at txindex 0, so it doesn't just continue across the blocks. Cool. And then there's some part of end blocker that, so this code I'm not going to go into too much because we don't actually use it in the tutorial version. But all it does is add the root hash because that helps with proving and exiting later on the root chain. Cool. So that was actually all of the SDK functionality in Plasma. So our contract is in here. So Plasma MVP.sol, it's completely filled in. And I can actually show you a little bit of the connection between our SDK sidechain and the root chain. So we have this type Plasma struct, which maintains a contract session in the client. So when we init Plasma, we give it a contract address and the connection to Ethereum. And this creates that session. And then from there, we can get deposits with a nonce. check if the TX has been exited. We can watch for deposits coming in from the root chain. We can watch exits coming in from the root chain so we can prevent any UTXO that has exited from being spent again. And we can watch Ethereum blocks, and that's useful for checking if something has been finalized or not. Cool. Does anyone have questions on like app, or does someone want to look more into how the Ethereum connection works, or do we want to start deploying? Deploy? Cool. So everything I've done will be in tutorial. So I'm actually just gonna, I know this works with tutorial, so I'm gonna git checkout. Oh. So I'm gonna check out to the tutorial version that I've already finished beforehand, just because I'm not sure if I covered all my bases, so I'm pretty sure this is correct with the tutorial version. So what we want to do is cd into client ls. Okay, so I didn't go over that, but in client, this is where all of our commands are. So you can send tx over here and check your balance. So these are like CLI commands that you have. And then the actual commands for starting the Plasma chain are in here. So that's in Plasma D. Plasma D is where you start the Plasma daemon, and Plasma CLI is for interacting with it. So I didn't go into any of the filling in the code here because it's largely using Golang's CLI libraries like Viper and Cobra. And that's like, if you learn about those documentation, you can kind of follow along and see what's happening here. But I'll leave that aside for now. So what I'd want to do is go install both my Plasma D and my Plasma CLI. Cool. All right, so another thing I'd want to do is start up Ganache, which is like a local Ethereum node that we're going to connect to. So we're not connecting to the actual Ethereum blockchain. We're connecting to basically our own version of the Ethereum blockchain just for simplicity. And I put -m equals Plasma because that'll make sure that all of our contract addresses stay the same. So if you put Ganache CLI -m equals Plasma, then you're going to have all of the same contract addresses and accounts that I have. Cool. So now we're listening on 127.0.0.1 on port 8545. So I first want to go into my contracts, and I want to deploy my root chain contract to Ganache. So I can do that with truffle migrate. If you're following along, you'll probably have to run npm install before truffle migrate. So my Plasma MVP contract address is this 0x5CA. That's where my root chain contract is stored on the Ethereum root chain. Cool. So let's see. From here, I'd want to run Plasma D init. So that created cool. So that created this folder, which contains all my configuration. I already have the filled out plasma.toml and genesis.json in docs, so I'm just going to copy them from there into here, and then I'll show you what they look like. so what I want to do here is, so one thing I need to do is just give my my tenement validator a moniker. What else would I need to do? Okay, so vi. Cool. So this is the Plasma configuration file. So my tenement node is the validator, so it's set to true. This is the file where my private key for the Ethereum node is stored, because I need access to it so that I can sign my blocks and submit them automatically. This is the contract address for the Ethereum root chain. As I said before, it's the exact same as the deployed, what we saw when Truffle deployed. So it's 0x5CAE, same address as before. The Ethereum node URL is where it was listening on, 127.0.0.1, 8545, with WebSocket protocol. And then I've just set minimum fees to 0 and Ethereum finality to 0 just for demonstration purposes. Okay, so priv1 needs to also be in here. Cool. So now priv1 is in here. So when I start my Plasma chain, it can read from here, read from that file. Okay. So should be able to run Plasma D-star now. Okay. I forget how to kill this. Do you remember which number is the process ID?
The second one.
The second one? Okay.
2214.
Okay, so p kill, then I just put that in?
I do kill minus 9.
Dash 9?
Kill, I don't know about p kill, but kill.
Cool. So now I want to deposit onto the root chain. So on the current version of our blockchain, you can deposit straight from the CLI, but on the tutorial version, you just can't. Or you can, but it's hard. So I'm going to deposit from my Ethereum wallet into this local chain. So if you want to, you can set your network to point to your own local Ethereum network. So CLI node. So what I do is I paste the contract address here. I also paste the ABI of my smart contract, which I've copied into here. It's very large. So I want to access that contract. Cool. So now I should be able to deposit now. So now I can use the Plasma CLI to import these private keys into. So these private keys were the private keys from my Ganache CLI instance. So I think it's the first and the third one. Cool. So now if I Plasma CLI list, I have both addresses in my key store. Right? Let's say I want to deposit from this guy. Yeah. So I'm depositing 10 Ether. What? 0TX has nonce of 1. That's interesting. Okay, so I want to access it by just giving it the private key. So I can do that. 0x8e is the second address, so it corresponds to the second private key. And then I can write 10 in here. So I'm sending 10 ether. Cool. So it's been broadcasted to the network, and I can see that's this transaction. OK, so now I've deposited. Now I actually want to spend my deposit. So I can look at Plasma CLI send. OK, so I need an address. So the CLI has been cleaned up.
That deposited into the root chain contract.
Yes. So we deposited into the root chain contract, and now what we're going to do is spend it on our Cosmos sidechain. So the owner of that address was 0x80. Amounts. So I can actually, with my contract, look at, so I think it was deposit nonce 1. I can read it, double check, yeah. So you can see the owner is 0x80. This is the amount in Wei. And then these are a few other fields. But let's copy that over. Let's say I want to send all of it to the other address. So 0 is the amount to, and we don't have a fee in the tutorial version. So I'm going to spend position. And you notice my deposit nonce was 1. So my first 3 fields are going to be 0, correct? Because when I spend a deposit, these first 3 fields are 0 in the position, and my deposit nonce is 1. Cool. So you can do that. And then 2, 0x4c9. All right. Awesome. So I got committed at block 322. That's the transaction hash. How do we know that this worked? We can check the balance of our 2 address. So at position 322, it's the first transaction index in the block, first output index, and it doesn't have a deposit num. And this is the amount it has. And now we can then spend this again. So
Updating state on the.
yeah, so this is all on the sidechain now. So what it did was.
So does the sidechain use SecP or there's usually there's 2 different key spaces there, right? There's Ethereum key space is SecP 256K1, and then usually Tendermint is ED25519.
Yes. Yeah. So.
Is it using the same key, or did it just share the private key?
Okay, great question. So Tendermint, the validator, is using ED25119, right? But the owners, and if you look at the owners.
So the signatures on the chain basically
Yes.
are done with the SecP. Okay.
Yep, so if you look at transaction on types, it's using a common.address, and the common.address is Go Ethereum common. And so we're actually using SCCP like as the users are using SCCP addresses. They're using Ethereum addresses, they're using Ethereum style encoding, and that makes it completely compatible with the root chain, Ethereum root chain. So even, yeah, you're right. Even though the Tendermint is using ED25519, with the Cosmos SDK, we can make the user level use whatever it wants.
So you guys going to contribute to Ethermint then?
Yes, when Ethermint comes, we're going to deploy it with Ethermint as the root chain pretty easily, I think. So yeah, so we can now send. So this is now a UTXO that completely exists on the sidechain. The root chain has no idea this UTXO even exists. So we can now continue to spend this thing on the sidechain. So let's say this time we want to split our amounts. So I'm sending 5 Ether to each account. And this time, what's my position? Well, my position is just this thing, 322.0.0.0.
Plasma CLI is talking to the Tendermint node over HTTP? Or
Over
client in there.
Yeah, the Plasma CLI is, well, this is the full node. Wait, where's the full node? This is the full node.
Plasma D is your full node, right?
Plasma D is my full node.
CLI is talking to Plasma D how?
That's a good question. Yeah, I think it is RPC.
So he's got two blockchains running. He's got the Plasma D basically, and he's got the hashes.
Yeah, so there are two blockchains running.
There's one blockchain left. Have you run any tests to see what the transaction throughput you get on the sidechain?
So we haven't been able to fully push the limits of it because we're still doing some internal testing and mostly focusing on fixing the UI and stuff. But it is a Cosmos SDK chain, so I would be very surprised if the throughput was not comparable to Gaia or another Cosmos SDK chain. But we haven't rigorously tested the throughput yet. And then now you can check the two balances. So here, this is the first output, 531000, and it has 5 Ether. And we can check the second output. Oh, nope. And here you can see transaction index didn't increment, but the output index is 1 because it was the second output. Cool. Does anyone have questions on anything? All right. Thank you guys for listening.
Actually, I have a question.
Yeah.
If you had a malformed block, the error handling is mostly avoided.
If we had what?
Say you have a block with an invalid transaction,
Mhm.
fails one of the checks.
Mm-hmm.
So you discard the entire block, is that right?
No. So when the validator is honest, transactions enter his mempool. So he has a list of transactions. He then will pick, say, 50 transactions out of that mempool to be in the next block. He runs anti-handler on all of them. And if anti-handler fails on one of them, he doesn't include it in the block. So a honest validator should not be including a transaction that failed on anti-handler. Yeah. Now it's possible that a malicious validator puts in invalid transactions and commits it and submits it to the root chain. But if he does that, then all of the full nodes will see it, and they won't send the confirm sig. And if they don't see it, then they're not going to send their confirm sig until they've seen the block and seen that it's valid anyway. So that's not a valid way for the operator to steal funds.
I missed the part about when does the interaction? Sorry, you are. I missed the part about when do you reconcile with the root chain? Like when in this flow? So
What do you mean by reconcile?
We've been spending these UTXOs on the sidechain, right?
Oh,
and
right.
At some point, you need to tell that contract.
Mm-hmm.
When is that interaction?
Okay, so the UTXOs stay on the sidechain up until the owner of that UTXO decides he wants to exit. So it's only when he wants to exit back onto the root chain that he reveals, hey, I have this UTXO on the sidechain. He submits a Merkle proof of inclusion that this transaction was included on the sidechain, along with the confirmed signature from its owner, from its previous owner. And then when that happens, he gets put into an exit queue. And if, for example, he tries to exit a UTXO that has already been spent, then there's a challenge exit function where any user can say, hey, you're trying to exit a UTXO that's already been spent. Here's my proof that you've spent it. And their exit fails.
Yeah, because the contract can't know the state of the sidechain at all.
No.
So it's just hoping somebody will catch before the exit happens.
Yeah, so we give a week between when your exit gets finalized. So you have a week to challenge. And so long as you give your confirm sigs out, everyone who has that confirm sig can challenge on your behalf. Yeah, and the Ethereum root chain knows the Merkle roots of every block. So the validator, when he's creating blocks, he submits the the root of the Merkle tree of transactions to the blockchain, to the root chain, but not actually what the transactions are. So then when you're making a exit, you're making a proof against that submitted Merkle root that the validator submitted.
Which the contract checks somehow?
Yeah, the contract does the Merkle proof verifying.
So every every tenement block, basically, the Merkle hash of that is committed to the root chain.
Every tenorment block that contains a transaction. So if there's an empty tenorment block, we don't submit that.
That seems like a lot of commits.
Yeah, so there's an optimization where we can either commit like 10 blocks at a time or 50 blocks at a time. That's fine. Yeah, it is a lot of commits, but you can kind of do them concurrently. And yeah, if you do that, then it's not a big deal. You can submit, we allow you to submit multiple blocks at the same time.
So the operator pays for those commits
Correct.
and transaction fees.
Ideally, the gas value of his submit blocks is outweighed by the transaction fees he collected.
Now, what if everyone on the Plasma chain exits at once? Are there like data availability?
Yeah, so that's like a mass exit issue,
Yeah.
which is somewhat of an open problem still with Plasma. There are a few ways that people have proposed to solve it, but yeah, we have not implemented any of those solutions because they're not fully fledged out yet.
Gotcha.
Yeah. Cool. Anything else? All right. Thank you, guys.